So today's talk is by Doug Wright, who is currently at Drexel University. I first met Doug when he was still a PhD student at Boston University. And I think he hated my guts for asking him hard questions at the end of his seminar, at the end of the conference talk I attended.
Still do.
What's that?
Still do hate your guts.
All right, good. And then after that, he took a postdoc at the University of Minnesota, where I visited him again. I took his course. And where Tom took his course. And then since then, he's been at Drexel, and he's going to tell us today about the challenge solutions of the Whitham equation. Thank you, Doug.
Oh, great. Thank you, Bernard. I don't actually hate Bernard's guts. I like Bernard very much. Thank you guys for asking me to do this. I've never done anything like this before, so it's going to be, we'll see how it goes. You can see my title of my talk here. It's about traveling wave solutions of the capillary-gravity Whitham equation. This is work done in conjunction with Matt Johnson and Atanas Stefanov. Both those guys are at the University of Kansas. So let's get into it. So this is Whitham right here. One of the great 20th century's leaders of nonlinear waves. He wrote this book, Linear and Nonlinear Waves, and he was interested in surface water waves, and the full Euler equations for that are relatively complicated to write down, and he was pretty interested in model equations. So he wanted to write down something that was simpler than the full system, but still allowed for complicated nonlinear phenomenon. Like he wanted to see waves break, and he wanted to see like waves that have peaks in them and stuff like that. So he really wanted something that captured that stuff better than something like the Korteweg de Vries equation would. So he had this idea about how to do that. So here's his model. Let's look at it very closely here. So here the unknown is u, and that's standing in for the elevation of the surface of the water at some position x at some time t. So this is a 1D interface here. And then so it's ut equal plus wu plus u squared x equals 0. So what is everything here? So probably the most important thing here is understanding what w is. So w is a Fourier multiplier operator. And so the way that you compute it is you take u, and then you take its Fourier transform with respect to the x variable. That's u hat. Then you multiply it by this tanh k over k under the square root thing. And then you inverse Fourier transform that. So that's the operator got it. So it's a kind of funny thing. It's not a derivative. It's not a local operator, but it's done in this somewhat strange way if you've never seen this sort of thing before. But it's pretty common in water wave modeling is to see stuff like this. Now, the idea here is that this equation, what I've called WE, it looks a lot like the KdV equation. If you took that operator W and you replaced it with the second derivative, it would be KdV, because there's that extra x derivative there on that second term there. So that would be 3 derivatives on the linear u term. But what Whitham did was he just took that third derivative and he mucked around with it so that this equation has the same dispersion relation as the full free surface Euler system does. Okay. So that sort of he's matching in at least an approximate sense, he's matching the linear behavior sort of correctly, like exactly. And then he puts on this KdV nonlinearity to keep some nonlinear stuff in there. Oh yeah, to be clear, when I'm talking, the sort of physical problem that's lurking in the background on this slide is that I've got a 2-dimensional fluid with a 1-dimensional surface. So it's like there's like a vacuum over the surface of the fluid. It's got the fluid has a finite constant depth at infinity. Like I said, the interface is one-dimensional. The only force at this time is gravity. So the only restoring force is gravity acting downward. The fluid's ideal. It's an irrotational flow. I've non-dimensionalized everything. There's no surface tension, so on and so forth. Okay. So one thing I always like to point out here is that, you know, Whitham, he just kind of wrote this down. He didn't do anything like too systematic to get to it. He basically just changed KdV so that the dispersion relation was exactly that of the Euler problems. So I kind of like that aspect of it. So, you know, if you're going to just make up an equation, right, you and you're going to say it has something to do with water waves, then you want to know if it works. Okay, so so here's the answer as to whether or not this equation is good for modeling. So this is some background work on this sort of equation. So first of all, the Whitham equation, it possesses solitary and periodic traveling wave solutions, which have the correct stability and stability properties, which is to say that, like, it has solitary waves in sort of parameter regimes where so does the corresponding Euler problem. It has periodic traveling waves with the right sort of frequency, and it has the right sort of stability and stability stuff. And this is, you know, relatively recent work by this list of names here. In particular, you'll see the names Grove and Vollen a lot, and Ernstrom a lot, and also Her a lot. Now, remember, Whitham was interested in having a model that.
Hey, Doug, I have a remark.
Yeah.
So you say it has the right stability properties. So I would actually disagree with that because it doesn't have the high frequency instabilities that the water wave problem does, because it only has one branch of the dispersion relationship. So the other water wave problem has non-modulational instabilities, also in shallow water, and Whitham doesn't have those.
Okay, I'll put some in my next slide. That's some of the correct stability and stability properties. Is that better?
Well, that's more accurate.
Works for me. It does do this stuff with the peaking and the wave breaking that Whitham wanted to see. So it has that sort of nonlinear phenomenon that he was looking for. And another thing here is that that's sort of important is you know, Whitham is in some sense proposing this as a replacement for KdV. I mean, it's more than that, but like he's sort of trying to do something that's a little bit better than KdV. So one thing that you can prove, or not, or that one can prove, this group of people proved, is that in the regime where KdV is a faithful approximation of the full Euler problem, Whitham does just as well. It doesn't do better; it does sort of the same. So that's a nice result. And then your fellow Seattleite, John Carter, did some work where he compared numerically computed solutions of KdV and numerically computed solutions of the Whitham equation with genuine experimental wave tank data. And at least for some of those experiments, you know, you're comparing your mathematical model with real experimental data. The Whitham one appeared to have done better. And you can go ask John about that if you want more details on that. Okay. So anyway, my opinion is that it's you know, it works pretty good. So that's we're going to keep on with it, talking about it then. Now, everything I set up here was, you know, trying to understand these this Euler system in the absence of surface tension, and so David Lange and Jean Clouseau thought that they could try to maybe like incorporate surface tension into the Whitham equation. So they did that in 2013, and they came up with what I'm going to call the capillary-gravity Whitham equation. So more or less, they did exactly what Whitham did, except that they modified that one term so that the dispersion relation coincided with the capillary gravity problem instead of just the gravity wave problem. And so the Fourier multiplier here, which now I'm calling M sub B, has this somewhat more complicated form here, but in it you can see that if you put this number B, if you put it equal to 0, you get back what you had before. So B is the measure of how strong the surface tension is. And I'm going to refer to it as the bond number. It might be 1 over the bond number, depending on who you talk to. I'll just call it B, I guess. But B is really a measurement of how strong surface tension is relative to gravity. Okay. So if B is 0, there's no surface tension. If B is like super huge, then there's a lot of surface tension. That sort of idea. Now, one thing I want to point out here is that if B is 0, that multiplier tanh k over k, that's bounded in k, right? It's tanh k is asymptotic to 1. It's got a 0 at 0, so the division by k doesn't cause you any problems. So it's just some bounded function of k. Whereas if B is bigger than 0, this thing is no longer bounded in k because, well, it grows, I guess, roughly like the square root of k as k goes to infinity. So it's more like a derivative than in the previous one. So it's got some analytic differences for the other one. But anyway, we'll get back to that in a little bit. So anyway, this was all set up to get the same sort of dispersion relation effect for the full capillary gravity Euler systems as Whitham's did for the gravity problem. Okay. So so this slide, okay, on this slide, I'm going to tell you about, okay, if you have a so let's say that you write out all the equations, the full Euler system for free surface capillary gravity waves. Again, there's a finite depth here, and it's an ideal fluid, all the same sort of hypotheses that I had before, except now I'm allowing surface tension to be present. So I want to tell you a little bit about some of the traveling waves that are known to exist in that system. So these are rigorous results for the big problem. So one of the earliest results is by Emick and Kirschgosser back in the 80s, and it says that if the surface tension effect B is bigger than a third. So in your head, you should be thinking of B as being bigger than a third as being like lots of surface tension. Okay. So if B is bigger than a third, if there's a lot of surface tension, then you have solitary waves of depression. Which just means that if you were like physically looking at the wave going by on the surface of the water, it would be like a little divot in the surface of the water as opposed to an elevated sort of thing like you're used to thinking about when you think about solitary waves. And these waves are subcritical. Subcritical just means that they go faster than what is sometimes called the critical speed, which when non-dimensionalized is 1, but in units is g times d, and then you take square root, where g is the acceleration due to gravity and d is the depth of the fluid. Okay? So they're sort of slow waves of depression, right? And that's if you have a lot of surface tension. If you have just sort of a medium amount of surface tension, so anywhere between where your bond number is in between 0 and a third, there was a bunch of work in the 90s originally by Beal and Son, and then later with important contributions by Eric Lombardi, that showed that there are what are called supercritical. Supercritical just means faster than that critical speed. Generalized solitary wave solutions. And I'll show you a picture of what that means in a minute, but you'll notice that word generalized is important there. I'll show you a picture of generalized solitary wave on the next slide. But the sort of where Atanas and Matt and I started is if people want to use this capillary gravity Whitham equation as a model for capillary gravity waves, it should have the same sort of behavior. Okay, so that's what we set out to do. Now, of course, the CGW equation is substantially easier than the full Euler equation for capillary gravity waves, but we wanted to get people interested in the modeling potentiality of this equation. All right, so let me show you a generalized solitary wave. So on the top of these two figures here, I've got the wave of depression, so the blue line is the profile of the traveling wave. So you see it goes down instead of up. Now in the bottom picture, the solitary wave goes up, but you'll notice it's got this ripple attached to it at the end state. So it's that's what they mean by generalized. That's sometimes they're called nanopterons. The idea is that you have this thing that looks like a regular old solitary wave, and then glued to it is this periodic wave of a much smaller amplitude. And it's of a relatively high frequency. And just to be clear here, the ripple, that's the end state ripple, is co-propagating with the solitary core. So if you were standing on one of the maxima of the little ripple, and then Bernard was standing on the top of the solitary core, the distance between you would not change. Okay, so everything is fixed in a moving reference frame. And that's okay. Is that okay? We good? All right, I think we're good. I don't even know if you're there.
Can I ask a question?
Sure.
Hi, Doug. It's Dennis. Is the ripple? Hey, good to see you. So the ripples lasts for all times. Is this known?
Yeah. The whole thing is frozen in the moving reference frame.
Okay. All right.
Yeah,
thanks.
So you're like in a speedboat, riding along with it. That ripple is frozen. Yeah.
Okay. Thanks.
Great. I can't see you guys, so I just so you know. Okay, so this slide is going to tell you what our results are. So these are results about the traveling waves in the simplified system. It has subcritical solitary as a depression when the bond number is bigger than a third. That's what Stefanov and I wrote, like sort of general theorem for traveling waves and equations like that are sort of the same rough form as these ones are. And then it turned out that Matt and I realized that work applied to the CGW equation. And then Matt and I proved that the sort of subcritical generalized solitary wave solutions are there when B is in between 0 and a third. So that is to say, we were successful in our goal of matching results for the simplified model to the full model. We got a little bit extra because the equation is a little bit simpler. Well, I don't want to say extra, but we got some stuff. One bonus we got was that for the waves of depression, the solutions are linearly stable. I'm not going to talk at all about that. I just thought it was worth pointing out. And then Matt did this nice calculation in the for the ripples in the generalized solitary wave case that says that if you just had the ripples alone, no solitary core, that would be a periodic traveling wave. And he was able to show that in the sort of appropriate parameter regime that they're spectrally stable. Again, I'm not going to talk about that, but the point is we're able to get at least a little bit of a start on stability analysis for these guys.
Hey, Doug, I've got a question.
We're not anywhere close to being done with it. Anyway, yes.
So I'm just trying to kind of get a little bit of an understanding here. So the waves you're looking at are not small, right? Because there's a solitary wave in there.
So.
Or can they be arbitrarily small?
The wave. Well, they are small. I'll show you this picture later on. So the ripple is much smaller than the core, but the core is small itself. So. Okay.
So yeah. So what I'm trying to understand is, how essential is the non-singularity that you, is it nonlinearity that you have? Because.
How essential is it? Not very.
Okay. Because in small solutions, you would expect that you're going to mimic the results from Euler because you get the same dispersion relation.
Correct.
Okay. So and then
yeah.
so if you changed the nonlinearity, if you made it a different power or something, would things be different?
Yeah, I mean, yes, they'd be different. I think if it was just a pure power nonlinearity, if you had a reason that you wanted to study that, I think you could repeat what we've done.
Okay.
I mean, the details would obviously change, but I think the big picture would not.
Okay.
Okay.
Thank you.
I haven't really thought too hard about that, so I could totally be wrong, right? It's not a question I'd consider. But the nonlinear, you'll see where, maybe you'll see where the square and the nonlinearity plays a role down the road.
Okay.
Okay, so, let me, I have one, this remark in red I like. So, so you can approximate solutions in the full Euler problem in an appropriate limit with the KdV equation. And it doesn't care what the bond number B is, so long as it's anything other than a third. Bigger than a third, less than a third, whatever. And that KdV approximation for capillary gravity waves predicts the wave of depression when B is big. And it does make a prediction about a solitary wave when B is in between 0 and a third, but it does not predict the ripples. It predicts genuinely fully localized solitary waves. So one thing from a sort of modeling perspective, perhaps, that the CGW equation has over KdV is that it has these ripples in it that are not present in the KdV approximation. Now, I don't know, KdV approximation is an approximation, and it's only supposed to be good to a particular order, and the ripples are very, very small, and in fact, they're much outside, they're much smaller than the order that you expect KdV to be valid at, so that KdV doesn't see it is sort of in some sense unsurprising. But maybe if you're just trying to get some phenomenological stuff going on, this equation would have a little bit more correct phenomenology. Anyway, that's just a thought that I had. Yeah, Arneson had some work on the CGW equation using sort of variational methods that proved a different sort of bunch of traveling waves that are called modulated solitary waves, which look a little different than what I'm talking about here. So I'm not going to talk about them too much or at all. But, okay, so let me explain to you what's going on here. So, like, how do you prove these theorems that we've got? So let's just get the governing equation for the profile here. So you put in your standard traveling wave ansatz. U is going to be phi of x minus ct, and phi is the profile of the traveling wave. You plug that into the CGW. Turns out everything's got at least one derivative on it, so you integrate once. You set the constant of integration to 0 because that's something you can do. And you get this equation right here. So it's mb minus c. C is the wave speed phi plus phi squared equals 0. To be clear here, mb is that Fourier multiplier operator. So this is a nonlinear, because of the phi squared, non-local equation, because mb is non-local. It's not an ODE, so you can't do like phase plane analysis to get the solution of this guy. You got to do something different. In this case, that something different is going to be sort of functional analysis and perturbation theory. So the first thing here is to, after you've got the governing equation, equation 1 here figured out, you're going to make what is often called, sometimes it's called a KdV scaling, sometimes it's called a Boussinesq scaling. I'm going to call it a long wave small amplitude scaling.
Hey, Doug, I have a question.
Yo.
Equation 1. So you put the integration constant to 1, which would work fine for the depression solitary wave, but what do you do with the ripples for the other one?
What are you talking about?
So how can you justify for the generalized solitary wave putting the integration constant equal to 0?
I don't really understand your question.
So to get to equation 1 from your starting problem from Whitham, you have to integrate.
But if a function solves 1, then it is a traveling wave.
But if I look at if I evaluate 1 at infinity,
if you evaluate 1 at infinity,
then and if phi goes to 0 at infinity, which is true for the wave of depression, then that's fine, that's consistent. But the limit at infinity for the generalized solitary wave is not defined, right?
I agree that the limit's not defined, but that equation is equal to 0 at infinity.
So can you in general, let me tell you the way I think the constant?
So if a function phi solves 1, then it is a traveling, then it gives the profile for a traveling wave, period.
Right.
Okay.
Yes, hello, Dr. White. I think probably Bernard's question is regarding equation number 1. The right-hand side could be non-zero constant.
Right, and you're able to absorb that into the left-hand side if you want by replacing like what C with something different.
Yeah.
Yes, if the right-hand side is non-zero constant, yeah, you can solve the traveling wave solution explicitly. A little bit tricky, probably very hard.
So choosing the constant integration to be 0 is actually not restrictive.
It's not really restrictive.
Okay.
Remember, I'm looking for traveling waves. Like I've said several times, if it solves one, it's a traveling wave.
Uh-huh.
Right, but your point is actually you're getting all traveling waves up to some transformation.
I didn't say that.
Ah, you just said that.
Okay, thank you.
Can I keep on going?
Please.
All right.
Sure.
So I'm trying to solve one. I'm going to make this scaling here. Okay. So so here epsilon is a small number. So I'm going to assume that the amplitude scales like epsilon squared. That's the epsilon squared in front of the capital phi. And I'm going to assume it's long wavelength. That's why it's epsilon y on the inside. And then you also scale your speed in this way, where it's 1. Remember, 1 is the critical speed. And this gamma b, I'll tell you what it is in a minute. It's just a convenient constant. So what I'm really saying here is c is close to 1. All right. Here this number gamma b is 1 minus 3b over 6. It just turns out it's convenient. But you'll notice that it changes sign when b goes through a third, which you'll remember that was an important number earlier. Anyway, if you do all that, then if you make that scaling change and you plug that into 1, you get this equation that I've called 2. So I've got some linear operator L epsilon b, I'll tell you what it is in a minute, plus phi squared equals 0. L epsilon b is a Fourier multiplier symbol, and it's just got this symbol right here. It's not so exciting. You can see that it's just made out of mu sub b. That was the multiplier before the scaling, with some epsilon stuffed in it and a couple other things stuck around. Okay. One thing I want you to note here, I said this already, is that gamma b is positive when b is in between 0 and a third, and when gamma b is less than 0, it's when b is bigger than a third, gamma b is less than 0. And so if you look at this hard enough, you'll realize that that tells me about the super subcritical thing. If b is bigger than a third, then the c I've got here is 1 minus something, and which means it's subcritical, and this vice versa for b in between 0. So anyway, you get this thing. Okay. Now that Fourier multiplier operator, it depends upon epsilon, and so you could do a naive expansion, like power series expansion in epsilon. If you do so, this is what you get. You get something like gamma epsilon b of k, something like minus gamma b 1 plus k squared plus something order epsilon squared. So if I just take that expansion, I plug it back into equation 2, and I identify capital K squared with, ik is like a derivative, so k squared is like minus 2 derivatives. And you rearrange stuff, you get this equation right here. Okay? And this is all formal stuff here. That order epsilon squared stuff could have some pretty toxic crap in it, but I'm just going to leave it out for the time being. So I take that, I put epsilon equal to 0. The right-hand side is now 0, and that left-hand side is the ODE, which gives you the set squared solution of KdV for its solitary wave. So this sort of formal long wave small amplitude analysis gives us a sort of leading order part for our proposed solutions that look just like we would expect in KdV. Going forward, I'm going to call that leading order part sigma b. The reason why this stuff is hard is that inside that order epsilon squared term that I just so cavalierly threw away is stuff that contains high derivatives. You'll note that the error term for lambda epsilon there has order epsilon squared k to the 4th, which corresponds to 4 derivatives. So if you have a small parameter multiplying a high derivative and then you throw it away, that's sometimes not a great idea. And that's where singular perturbation theory comes in. All right. Now, I'm going to very quickly talk about the wave of depression thing here. It turns out that when b is really big, that symbol lambda epsilon k is strictly bounded away from 0, and that operator L epsilon b is invertible. So you can, my equation here is L epsilon phi plus phi squared equals 0. I can rewrite that in this just by inverting it and getting that equation. And then there's this nice fact that the inverse, so 1 over lambda converges nicely to minus 1 over gamma b 1 plus k squared, and that convergence is uniform on all of R. And so it turns that essentially what I'm trying to say here is by inverting that L epsilon, you kind of get rid of the singular perturbation. It's pretty nice. So that that operator converges nicely in the appropriate operator topology. Then you set it up as an implicit function theorem argument. Everything I set up to here is just saying that I have a solution of this nonlinear equation n equals 0 and epsilon equals 0. That's what so I've got a solution at epsilon equals 0. You compute the linearization at that point, like you're supposed to do to do the implicit function theorem. You get this operator right here, which maybe at this stage doesn't look so good, but if you stare at it long enough, you'll realize that it's just morally the same as the linearization of the profile equation for KdV, and that's known to be invertible on like invertible functions in, say, HS. So all that means that you can use the implicit function theorem to continue the solutions to epsilon greater than 0, and that's how you get the waves of depression. This strategy was inspired by this work by Frizeka and Pego in 1999 to prove the existence of traveling waves to the Fermi positive Ulam model. So that's sort of the thing that I knew when Atanas was talking about this equation at some meeting, and I put together this idea based on the marriage of those ideas. Okay. So what I'm really saying here is that the waves of depression are sort of, in a vague sense, relatively easy to prove the existence. You just are using really the very vanilla implicit function theorem. Okay. This doesn't work when the surface tension is small, and that's why the ripple appears ultimately. And let me explain what's going on here. So remember, my equation was L epsilon phi plus phi squared equals 0. So let me just consider a slightly easier problem. L epsilon br equals j. So j is just some given function. All right. So I'm just really investigating, can I invert L epsilon? The inversion of L epsilon played a role in the b greater than 1/3 problem. So I want to talk about that. If you Fourier transform that equation right there, the L epsilon turns into a lambda epsilon, and the r turns into an r hat, and the j turns into a j hat. And well, if you look at a graph of what lambda epsilon b looks like when b is small, it looks like this function right here. And that function is negative when k is small, and it's large when k is large. So turns out it has 2 zeros at some number, which I'll just call k epsilon for the time being. So if I evaluate the equation lambda epsilon r hat equals j hat at this special point k epsilon, left-hand side is 0, and so what we find is that j hat at k epsilon equals 0, which that's a restriction on what j can be, right? So I can't, it's kind of a characterization of the range of L. That's what I'm saying. The range of L is roughly those functions whose Fourier transform vanishes at the special number k epsilon. Importantly, L epsilon is not surjective. It is injective because the only thing that goes to 0 is, well, the only thing in like L2 or HS that is L epsilon applied to is to get 0 is 0, but it's not surjective. So you need like a solvability lemma. So I'm not going to try. I don't want to be super technical with all this stuff, but I'm going to use these function spaces here. So E stands for even, S stands for regularity, and Q stands for decay rate. So a function is in this ESQ space if that function, when multiplied by cosh of Q times X, lives in HS. And it's even. So roughly speaking, this is ESQ is those functions which are S times differentiable, and the function and its first S derivatives converge to 0, roughly speaking, like e to the minus qx as x goes to plus infinity. So they're rapidly decaying functions on the spatial side. So the thing here is that I can solve an equation L epsilon u equals j, where j is an ESQ, if and only if the Fourier transform of j at the special frequency k epsilon is 0. I'm going to denote such solutions L epsilon inverse, and the solution operator gains a half a derivative. That's not so important, but it is true. Okay. So I can find a ES plus 1/2 Q solution of L epsilon U equals J, provided J is in ESQ and has this Fourier transform condition being met. All right. You get some estimates. That's not so exciting. And you use this using a lemma from a paper by Tom Beal from 1980. Kind of a nice little lemma. You can give it in harmonic analysis class if you want. There's a problem. Okay, so let's go forward here. So okay, so there's this frequency k epsilon at which lambda epsilon k epsilon equals 0. Another way of thinking about that, if you sort of unravel that on the space side, what it's saying is that L epsilon kills cosine of k epsilon x, right? So that's kind of another way of saying the same thing. Now, I was talking a few minutes ago about how epsilon was injective, and it is injective, but it's injective on the class of L2 functions. Of course, cosine is not an L2 function on the real line. So there's a whole issue here about what function space you're dealing with. Okay. And then another point of view on this is that what I just said here is that cosine k epsilon x is a periodic solution of the linearized problem. The linear problem was L epsilon phi plus phi squared equals 0. If I linear that, I get L epsilon phi equals 0. So what I've got here is this thing that's giving me my surjectivity issue is also telling me that there are periodic solutions, at least for the linear problem. Matt and Vera used that sort of idea as a jumping off point to prove the existence of small amplitude periodic traveling waves for the nonlinear problem. I'm not sure how they did it, but I think that they did something along the lines of a bifurcation from a simple eigenvalue sort of argument. I'm pretty sure that's how they did it. Okay, so you have a sort of a family of small amplitude periodic solutions to the nonlinear problem, and here's how I sort of write it down. So I've got solutions phi that are look like A times PA of X. And so what is A? A is the amplitude. So A comes in some range, but there's some interval in which where this is true. PA is roughly cosine. That's what we expect it to be, plus some small, some order A perturbation to that. And these waves have frequency k epsilon A, where when A is 0, it's just the genuine k epsilon that we saw from earlier. And then because it's a nonlinear problem, the frequency might change a little bit as we change the amplitude, but not by very much. Okay. So we have these periodic traveling waves for the CGW equation. In that paper by Vera and Matt, they do a whole study of the spectral stability of these guys. Now, the way that you find generalized solitary waves is to make something called a Beal's ansatz, or what I call Beal's ansatz. So you write your profile phi as the sum of sort of three things. One is the KdV-like set squared guy, sigma b of x, that you computed formally like 20 slides ago. To that, you add u of x. U of x here is just some localized error function. I'm thinking of it as being small. And then you append to that the ripple. All right. So why do I add the ripple there? The idea here is that I have two unknowns now. I have the error function u that I need to figure out, but I also didn't tell you what the amplitude of the ripple was. So I've got two unknowns here: u, which is like function, and a, which is just a number. If you plug Beal's ansatz into the governing equation, and you isolate everything that's linear in either of the unknowns, either u or a, you get this equation right here. So it's L epsilon u plus 2 sigma b u plus 2a phi b p0. Remember, p0 is like that cosine, sigma b is like the set squared, and then everything else goes into this junk term, Okay, so the right-hand side is all this junk that's like nonlinear or small for some other reason. So I'm going to act like J is sort of innocuous. So I want to solve this equation for U and A simultaneously. So let me just act once again like J is some specified function, and I want to see if I can solve it. Now I know that if I don't have those other two pieces there, L epsilon U equals J, I know that I can't do it because of my solvability condition, but now I've got a slightly different system. So I apply the Fourier transform to this. If I try to apply the Fourier transform to this and I evaluate it at the special frequency, the L epsilon part goes away. That's what happened before. And so I get these three terms. Those are the second two terms in the equation on the right-hand side. And the nice thing here is, as written like this, I can solve that equation for A. So I solve for A. So now I know what A is. So if you give me J, I can now figure out what A is in terms of J and U. So I sort of got rid of one of I got rid of one of my variables. I already know what A is. And in particular, I've basically met the solvability condition by this choice of A, the solvability condition for L. One thing I should point out here is that I divided by something, and it's easy enough to show that that thing is positive. So strictly positive. So it's kind of all downhill from here. What I'm going to do here is I'm going to sort of use that formula for A that I've got to define a projection here. So this projection here is really just a technical way of saying I solve for A correctly. If I apply that operator to my equation, this projection operator pi epsilon here, I get this equation here. Pi epsilon by construction, if you apply pi epsilon to any function, it meets that, and then you evaluate that at the critical frequency k epsilon, you get 0. So again, this is really just solving for A. So it's not so exciting. It's just sort of a way of packaging everything. But written this way, I get L epsilon U plus pi epsilon blah, blah, blah equals pi epsilon J. And then it turns out that I can invert L epsilon on this. So I do so. I get this equation right here. And the sort of very technical thing at the real heart of this whole paper that you have to do a bunch of complex analysis to get is that that inverse operator L epsilon B inverse, when paired with the projection, converges in the operator topology to this operator right here, minus gamma B inverse 1 minus dx squared inverse, which is a pretty benign operator. And basically what happens is you're desingularizing that division by 0 that was worrying us earlier. So with that, then you replace the L epsilon inverse pi epsilon with its limit. You get something that looks like this. On the left-hand side, if you apply 1 minus dx squared to that, you get an equation that looks like this. Again, that's exactly the linearization of the KdV equation on the left, or pardon me, the profile equation for KdV on the left at the traveling wave, and it's invertible. So then you solve for U. So you can solve any linear equation that looks like this, and then you solve the nonlinear problem by iteration. It's really just the Banach fixed point theorem. So that's how you go through it. Let me just talk about some of the technical challenges, and then we'll be done. The spatial exponential decay of the core is tied to the analyticity of the Fourier multipliers. And so you really need to understand the Fourier multipliers very well. So you spend a lot of time doing what is essentially like differential calculus with this funny operator. It's not so hard, but it takes a lot of time. You need uniformity in epsilon of everything. One of the things that I didn't really get into here is that this critical frequency k epsilon is large in epsilon. And so that creates large constants that pop out in various places. Fortunately, every time you have a large constant, it multiplies something that's small. So it all works out, but there's many places in it where you think that you're doomed, but then you get lucky and it doesn't work out. the iteration argument that I was discussing earlier is got some issues because that right-hand side turns out it's not continuous in the operator topology, because the frequency changing, as the frequencies of the periodic waves change with A, that creates some technical difficulties. But okay, you get around that anyway. You got to do something that's not so exciting. And the last thing I want to, well, maybe not the last thing, but one of the last things I want to say here is a byproduct of the proof is that you get a formula for A out of it. And it's pretty horrible, but you still get a formula for it. So it turns out that A is the Fourier transform of something, this thing that I've called gamma of U, evaluated at the critical frequency. That gamma U thing, it's a smooth function, and the critical frequency is large. And so the Fourier transform at large frequencies of smooth functions is small. That's oscillatory integral estimates. And so a byproduct of all this is that A is, it's very small indeed. It's beyond all orders of epsilon. Let's see. So we got just a couple minutes. Okay. So one thing we'd like to do is get better estimates on everything. A really hard question is to answer what happens as the bond number goes to 0. So here I fixed the bond number and I've basically taken the amplitude to 0. What you could do instead is send the bond number to 0 and see if your solution, these nanopterons that we can construct here, converge to the solitary wave for just the Whitham equation. So does the ripple vanish in that limit? I mean, one expects that it does, but you'd have to prove it. And then, I really like, this is my very exciting final statement here. So one thing about the ripple is that it goes forever, right? It's spatially. And so you sort of like has infinite energy, right? So in some sense, these things are not so physical. I mean, you could argue one way or the other, but they don't have finite mechanical, or they don't have finite energy, so to speak. So you might say, well, let me just ignore the ripple. You just told me it was exponentially small anyway. So what you might do is you solve the capillary gravity Whitham equation with just the core as the initial condition, no ripple, all right? And ask what happens. And so if you do that, and hopefully this video will run. So that's what I've done here. So in this video here, I've numerically computed solutions of the capillary gravity Whitham equation with an initial condition, which is more or less that sigma b thing. It's just a it's just a set squared, okay? And then I'm going to let it run. So then you let it run, okay? And so you see it propagates to the right, but I've zoomed in here. The bottom thing here is just a zoom in of that red box in the top one. And you can see that it spits out this, this high frequency thing. Let's see it again. Notice it's 5 orders of magnitude smaller than the wave itself. And that never, no matter how long you run this sort of just keeps on happening. It keeps on spitting out this small amplitude periodic thing to the right. And well, that's weird. And it sort of is sucking the life out of the core. And if you let it run long enough, you'll see that the core shrinks very slowly. So I don't know how to prove anything about that, but that's what's going on. And that's what I've got to say. So thank you. I was worried that you had all left.
No, everybody's still here, including the aforementioned John Carter that you talked about.
Well, you know, John's an advocate for this sort of equation, so.
Right. So any questions from anyone?
Hello, Dr. Wright. I'm George Chow from University of Texas.
Hello.
You know, hi, I think we saw each other before. Let me open my camera. Yes, that's me. Very interesting talk. I do have a couple of questions to ask you. probably you'll find something interesting. I saw in the very beginning you mentioned some peaked solitary waves would be derived from the model. So my question for you first, in what case that peaked solitary waves would be derived from the model?
That's a good question. So that work was, I'm sadly not, I'm going to get it all wrong, okay? So let's see what my notes say. So the peaking stuff was by Ernstrom and collaborators. And, I'm not really, I haven't read those papers carefully. I'm not exactly sure how they prove this. So I only know that they're basically able to prove that there's a solitary wave of, I think it's of largest height that peaks, sort of like in the Stokes wave sort of way. But I don't know the details.
Okay, I see. Yeah, second question is, for that model, it's called CGW model.
Yes.
When you take the integral after you reduce the PDE to ODE.
Sure. Well, it's not an ODE, but okay.
Yeah, right. Did you find all possible traveling wave solutions?
Oh God, yeah, no way. I mean, maybe, but there's nothing in our analysis that would indicate that that's the case. Yeah.
Okay. Thank you.
You should take that one.
So actually, if I may add something to that, I think you kind of have, because you can just do a vertical shift on the solution to get rid of that constant.
Oh, okay. So okay, and that just changes the speed c, right? Is that
right? Correct.
That okay? So, but then there's the question of all solutions of one, right?
Yeah, right. So yeah, my statement is that one is not restrictive.
Yeah. So let's say one is not restrictive. There's still nothing. There may be other sorts of solutions to this that our analysis doesn't find. I mean, of large amplitude or in a different scaling regime. There's no way. Everything we do is perturbative. So you're really only sort of exploring a small volume of solutions.
Dr. Wright, I also have a question. A lot of your analysis here applies to looking at basically the scalar equations, but if you were to do something like a Boussinesq Whitham system, would you expect to find similar solutions there? And
yeah,
some of your methods apply to those equations.
Yeah. So, so first of all, I think you can apply this method to a system because, well, I mean, this methodology that I described for you, was borrowed from Veal's original proof of the full system, which is of course a big system. So it's not really, there's nothing special about the scalarness of it. This works fine for systems, and there's not just Tom's work on the capillary gravity wave problem. Me and several collaborators did a similar sort of construction for solutions of Fermi pasta Ulam type equations, which are also systems, as it happens. So that's not a problem. The real thing, the thing that, let me show you the picture. So when you look at how do you know if you're going to have this sort of behavior? Right? So that's like how do you know if you're going to have a ripple, right?
Mm-hmm.
And the answer is really when you look at the dispersion relation. Roughly speaking, if the dispersion relation, which is kind of what I've got graphed here, but if it's equal to 0 somewhere, that's kind of you kind of get these things. And when I say it's equal to 0 somewhere, I mean somewhere other than 0.
Mm-hmm.
You need a little bit more than that, but you basically stare into your dispersion relation, and there's a few things that happen that, roughly speaking, will give you this idea. Really, what I think the correct technical way to say it is that if the dispersion relation has a phase speed which is somewhere equal to the wave speed that you're looking at, then you should expect to see this. that's a little. I'd have to be a little bit more careful when I wrote it down, but that's the my sort of in my head my rough way of saying it.
Sure. A follow-up question to that is then if you do consider, say, like a Boussinesq-Whitham system or something like that, and now you have two branches, you have the full dispersion relationship of the Euler equations, and you're trying to look for where the zeros are of that dispersion relationship. Do you expect to find that maybe if you do have these generalized solitary waves, maybe for some whatever reason, well, I guess they can't because they're traveling waves. But would you expect anything different to pop out of that, just given the fact that you'd have two different branches?
No.
Okay.
I think that the I mean, I could be wrong, but the FPU models that I've dealt with, and of course the full Euler equation that Beal and other people dealt with, also has multiple branches. And all that work came first, and this was sort of, nothing was different in this than those ones.
Okay.
So I think it'd be a great problem for the record. I think that sort of sort of thing, I think you have some technical challenges. I think it's totally doable. I think it'd be a very interesting problem.
Thank you.
Yep.
All right, do we have any more questions?
Yeah, I have one. So, Doug, there are solutions of KdV that do look like solitons, like say superimposed on a genus 1 background. I wonder if there's any.
I don't know what that means. They have I'm guessing they have a non-trivial time dependence. Is that right?
Yes, but you might be able to get them to translate at the same speed. Can't?
No. Well, you know, the base thing allows KdV.
They travel at the same speed they solve the ODE, right?
But if I do dressing and I stick a soliton on genus 1, I can change the genus 1 speed.
But you're going to run into the same problem now. You're going to have solids travel at the same speed.
Not convinced, but
I'm very confident.
okay. So never mind.
But they're right, yeah, conceptually they're very similar. Okay, well, thank you very much, Doug.
Thank you very much.
Okay, if convenient, would you please send me your PDF file of your talk?
Sure. I'm sorry that you told me your name, but I can't see you, and I didn't write it down.
I left a message in the chat channel.
Oh, okay, sure.